sequence, right? And those genes, the DNA is transcribed to make RNA, and then that RNA is now translated to make a protein. So the proteins are the working pieces of the machinery of the cells that make your cells work. The genes and the DNA code for these proteins. We have about 20,000 genes. I'll talk a little more about that. There's about 20,000 different genes, protein coding genes. So you have about 20,000 of these in the human genome. Just for example, to help sort of bring this, genes like myosin that make your muscles contract, right? They make the protein that makes your muscles contract. Hemoglobin that we think about that transports oxygen throughout our blood. The CFTR, this is the transporter that your lung can transport potassium, and this is what is detected in cystic fibrosis. Dopamine receptor, this is in your brain, right? This is just some examples of the genes. I can give you one list of 20,000, right? So maybe with this information, we can think a little bit about how you could have two different cell types from the same DNA, right? Think about a neuron. It's pretty different from a blood cell, right? This is sort of think of some immune cell in your blood. This is just schematic. Let's say the genes are like light bulbs. In your neuron, there's going to be some set of genes that are on, others that are off. And you might expect to see a neurotransmitter or two that's on in your neuron, right? And it's making protein, right? The other genes aren't making any protein, they're silenced. And this is why, this is a neuron. In contrast, you look at a blood cell, they have same genes, right? Same genes, but they turn off and on different ones, right? Now they're turning off this neurotransmitter, but they're turning on some other gene that is making an antibody that your immune cells need to go around and fight off pathogens, right? So this is just a very simple picture here. And actually, this concept is not so new. It was actually intuited, 60-something years ago by Conrad Waddington. This is actually before we really knew about the DNA or how this coded proteins. But Conrad Waddington sort of coined this concept of epigenetic landscape or epigenesis, where Conrad reasoned that, at the beginning there's a cell. And through the process of development, this cell sitting at the top of some hierarchy will kind of move down these sort of energy, minima. Think about a ball rolling down a hill, and give rise to the different cell types in an organism. And this turns out to be suddenly accurate for something that was hypothesized in 1949. And, this is sort of another picture of that. But now we realize that, these cells at the top of Waddington's landscape are these pluripotent stem cells or embryonic stem cells that, haven't decided their fate. Their options are open. These cells, through the process of development, and Conrad Waddington called this epigenesis, over development will turn on and off different genes and ultimately sort of fix those states, whether they be sort of mesoderm or endoderm, different types of cells. And I kind of show this at the bottom just to tell you this is the diversity, right? And this is sort of a concept that is with the heart of the field of epigenetics as we begin to think about how, again, one genome can give rise to so many different cell types. At this time, we didn't really understand how the genes were coded. We didn't know DNA, but now that we've learned, we can get a lot more information. We begin to understand how is it possible that this orchestration of events can proceed. That's on the human genome, right? So what is in our genome? This is kind of a fun picture because this is our director, Eric Lander, and Jim Watson there, who's Watson and Crick, of course, who figured out the double helix. And this is Francis Collins, who's the director of the NIH now, and Dr. Paul Waterston, who was a visionary in this process now. And Seattle published the Human Genome Project in about 2003. So it's sequenced for 3 billion bases. This is what is in the human genome. It's 3 billion letters of sequence. And what this is, if you look at this, it's pretty hard to interpret this book. But, it wasn't so hard to look for sequences that look like they could code for a protein because there's especially the DNA, these triplets, and you know what the triplets are in the DNA that will lead to certain code for certain amino acids, code for certain types of proteins. So you can actually go through this draft of the human genome and you can find the genes. And I think people were betting a lot at the time. Eric tells me that there was this whole betting pool where, some people thought there were, 15,000 genes, but some people thought the humans were so complex they must have more genes, and the numbers went up. Somebody thought there was 130,000 genes. But in the end, the answer was kind of boring. The answer was, in this 3 billion bases of DNA, there's only about 20,000 protein coding genes. It's not that much more than in a fly or a roundworm. But here's, I think, one of the most striking observations here, and that is that those genes, those protein coding genes, account for just 1 or 2% of the DNA sequence. So, what is the other 99%? And, to me, that was one of the most compelling and interesting questions that came out here. People thought, does it matter or junk DNA? I'll revisit some of these terms that we've evolved our understanding. But this is a really interesting question. If you think about DNA and purpose is to make a gene, to make a protein, and you realize that only 1% of your genome does that. So, I'll give you some more information on why that's probably important and how when I get into it, there's something more than the genes. And it comes actually from genetics. So I'm going back to genetics for a little bit. And, what causes disease? And we know of, here's your sequence of your genes, and there are diseases caused by mutations in the genes. And there's quite a few of them. They're often called monogenic diseases because there's an inheritance pattern. It's pretty simple inheritance. They're dominant or recessive. One gene's involved. I'll give you some examples. So cystic fibrosis, I already mentioned, is a mutation in the transporter, and that's what causes cystic fibrosis. There's sickle cell anemia is another example. There's a hemoglobin mutation. Duchenne muscular dystrophy. I can give you a bunch of examples. There's a fair number of examples. Eye color is kind of a monogenic trait where you inherit it. And it's one gene. It's a little more complicated, but it's not so much more complicated. So this is great, but there's a problem. This is the minority of cases. The vast majority of diseases that are a burden on society that we think about don't fit this simple model. Rather, they're complex human diseases, and it's not one mutation, but there are scores or hundreds of different mutations that are somewhat common in the population. That if they combine in the wrong ways, we don't really understand exactly which ways they combine, you end up with disease. And the examples are diabetes. This is a complex disease. It's not one mutation. There's many that contribute to this. Schizophrenia, multiple sclerosis, cancer, and I could go on and on. And we think of these as you might say polygenic or complex diseases. So the other picture I showed you, where it's just a gene that's a little simpler.